So in chapter 4, we're going to be looking at chemical reactions and just different types of reactions, and we'll be taking reactants and making products. But the first thing we're going to do is look at certain reactions, and all we're going to have to do is be able to tell what type of reaction it is based on the chemical equation. So we're going to look at combination and decomposition as well as combustion here. So combination reactions, they just have one compound being produced from two or more reactants. So remember when we looked at chemical equations, we talked about how the arrow is very important. So to the left of the arrow are reactants, to the right are products. So this combination reactions aren't too bad to look for because you just have to look for that one product, okay? So only having one thing in the product tells us that's a combination reaction. Okay, decomposition reactions are the opposite. So we have one reactant going to two or more products. So again, not too bad. They're pretty easy to look for. And usually with decomposition reactions, that requires heat. And this little triangle that's supposed to be above the arrow, and it's not, is symbolizes heat. So usually decomposition reactions need heat to begin the reaction. So again, all you have to do is look at the equation and tell me if it's combination or decomposition. Okay, so combustion I also threw in here, so that's actually not in your homework, but I do want you to know what a combustion reaction is. So combustion reaction is a rapid reaction with O2, so oxygen, and it produces heat and light. So all you have to do for a combustion reaction is look for O2 on the reactant side. Okay, it has to be on the reactant side. So here we have O2, here we have O2, so we know we have a combustion reaction. But also, if you notice, we have two reactants going to one product. So this is a combustion reaction as well as a combination reaction. So same thing here, two reactants going to one product. And actually, this reaction right here is the one we'll be doing for our empirical formula lab. Okay, so also we also have a combustion reaction down here, but here it's combined with what we call hydrocarbon. So hydrocarbon is just carbon and hydrogen in the molecule. Now, sometimes they'll throw in oxygen too, and that's fine. But what I want you to remember here is when hydrocarbons react with O2, they always produce CO2 and water. It does not matter how many carbons or how many hydrogens you have. As long as they're reacting with O2, they're going to produce CO2 and water. The displacement reactions we're going to look at. So with the single displacement, again, that's one you're just going to have to recognize that it's a single displacement, but the double displacement reactions, we're actually going to talk a lot about those, okay? So single displacement, you have one reactant that's all by itself right here, and then another reactant that's combined, it has two things in it. So a lot of times if you look, at the equation below it, so a lot of times it's a metal that's all by itself. So here's copper that's all by itself, and then we have a metal in solution. So silver is actually in solution because remember AQ stands for aqueous. So we have a copper solid and silver that's in solution. Now they react and they just end up switching places. So here's silver solid, and then now copper is in the solution. Okay, so they're just swapping places. So this is a little bit easier to recognize because you have that metal that's all by itself. So if you were in intro at Rose, we did this in the lab. We did a bunch of single displacement reactions that they're pretty neat to watch the metals actually switch place. Okay, then double displacement, we have two things switching. Okay, these are also called metathesis reactions. So here we have AB, let's try that again. AB and XY, okay? And they switch. So A is now going to be combined with Y over here, and X will be combined with B over here. So they are switching. So I always say the cations, which are A and X right here, A and X, switch their anions Y and B. So again, we will look at the double displacement reactions a lot in this chapter. So here's the three types of double displacement reactions. We have precipitation reaction. So you can see with the precipitation reaction, here we have lead and potassium. Those are our cations. And then they switch their anions. So over here we have potassium with nitrate and lead with sulfate. So they're just switching. Okay, what makes it a precipitation reaction is it produces a solid. So precipitation, it means it's forming a precipitate, which is a solid, okay? So if you have a solid as your product, you know it's a precipitation reaction, because over here we've got AQ, 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 and then one solid, okay? So that's, again, just look at your product. Okay, for the acid-base reactions, we have an acid, which we talked quite a bit about in chapter 2. We have base right here, which we haven't really talked a whole lot about. We'll get more into it in this chapter, but bases produce hydroxide ions and water. So we know that NaOH is dissolved in water because it's AQ, right? It's aqueous. So OH is going to form in the water. So we have an acid and a base coming together, and it's always going to produce water and a salt. So the salt just depends on what acid and base are combining. So water and a salt are always produced. Okay, and then the last one I think is the most difficult of the three, but this one is the gas-forming reactions. So in this, we always do produce water, and I'm not sure why. There's a question mark. That should be an L. But we produce water and we produce a gas. So here is our gas. So when we get to these little, later, I'll tell you why they're kind of tricky. But that's why we know it's a gas-forming reaction, because it does produce a gas. Okay, so in this one, we're going to classify each equation as combination, decomposition, single displacement, or double displacement. Okay, so I don't have any combustion reactions in this one. Okay, so I have two reactants forming one product. So that's our combination. Okay, here we have two reactants and two products, and you can see here's our cations, and they switch their anions. Okay, cations are switching anions, so this is going to be our double displacement. Okay, double displacement. Okay, and then here we have a metal all by itself, and then another metal with a compound, and they switch places. So we know that this is a single displacement, because we just have one thing switching places. Okay, then we have one reactant going to two products, so that's decomposition. And last of all, two reactants going to one product, another combination reaction. So again, all you need to do with these is recognize what type of reaction it is based on the chemical equation. So double displacement we'll do a whole lot more, but for now, just recognizing what type of reaction it is from the chemical equation. Okay, so before we get into the double displacement reactions, we need to talk about solutions. So a solution is just, let's see here. Here we go. A solute plus solvent. So remember, a solution is another name for homogeneous mixture. So right here we have salt being dissolved into the water. And when that happens, we know the salt's going to dissolve, and the salt is considered the solute, and that is being dissolved into the solvent, which is our water. Okay, so those are the two things for solution, solute and solvent. And anytime we dissolve something in water, it's always referred to as aqueous. Okay, we're going to be looking at different types of electrolytes. So we're going to talk about strong electrolytes, weak electrolytes, and non-electrolytes. So an electrolyte is just a compound that dissolves in water and it forms ions or hydrated ions. So it'll increase the electrical conductivity of water. So pure water by itself is a poor conductor of electricity. But when I put those hydrated ions into the water, they have charges, and so those charges actually make it possible for electrical or to conduct electricity. Sorry, I couldn't think of what I was saying. So strong electrolytes we're going to see will completely dissociate in water. So dissociation just means they break up into their ions. Weak electrolytes are only going to partially dissociate, and then non-electrolytes are going to dissolve, or they might dissolve, but they won't dissociate. So we're going to talk about all three of those. So strong electrolytes completely dissociate when they're dissolved into water. So what that looks like is this. Okay, I have sodium chloride. I put it into water. I know it's going to dissolve. It's just table salt. But in water, it actually produces sodium ions and chlorine ions. So I'm just going to draw my little beaker here. So when I put the salt in, I just get a bunch of sodium and chlorine ions in solution. Okay. So there's three different things that are strong electrolytes. Soluble ionic compounds are one. So we know what an ionic compound is. We learned in chapter 2, ionic compounds contain a metal and a nonmetal. And solubility we haven't really talked about yet, but we're going to get more into that for this chapter. So you'll be able to recognize, number one, is it an ionic compound? Yes. Number two, is it soluble? So we'll be able to look at that here in just a little bit. Okay, strong acids. Okay, we talked about strong acids in chapter 2, we talked about acids. Now, strong acids are all right here. So the difference between a strong acid and a weak acid, to tell the difference, we just memorize those strong acids. Okay, so memorize that list right there. Strong bases. We haven't really talked about bases, but I told you just a minute ago that a base is when we produce hydroxide ions in water, okay? So this is your list of strong bases. You also need to memorize this, okay? So let me write this down. Memorize. Okay, you won't need to memorize the soluble ionic compounds, but you will need to memorize strong acids and strong bases. Okay, for the strong bases, whenever OH is paired with anything from group A, it's a strong base. Okay, so all you have to do is look at your periodic table, see what elements are in group 1A, and put an OH with it, it's a strong base. Okay, then calcium, strontium, and barium are all from group 2A, but it doesn't have magnesium and beryllium in that list, okay? So only calcium, strontium, and barium, when they are combined with hydroxide, are they strong bases. So again, they just completely dissociate in water. So just to give you an example here, you know, if I have, let me go back. Oh, let's do CaOH2. Okay, when I put that into water, it's going to produce calcium ions, and we have a 2, so I'm going to put that out here, hydroxide ions. Okay, so it does the same thing. It just breaks up into its ions. Okay, weak electrolytes don't do that. Weak electrolytes only partially dissociate. So weak electrolytes are weak acids and weak bases. So if you know your list of strong acids, anything else is going to be considered a weak acid. So make sure to memorize those strong acids. Okay, so partially dissociate. So here's nitrous acid, right here. Okay, it dissociates into hydrogen and nitrite, but if you'll see, the symbol is different, right? It's not just an arrow pointing to the products. It's an equilibrium symbol. So HNO2 breaks into hydrogen and nitrate ions, but then the hydrogen and the nitrate come back around and form HNO2. So in our beaker, we're going to have all three of those things present. So we'll have hydrogen ion, nitrate ion, sorry, that is a nitrate ion, and then we'll have HNO2 all together. Okay, so all three. So that's exactly what the weak bases do as well. So we have ammonia and water coming together to form ammonium and hydroxide. So remember, a base produces hydroxide ions in water. So they come this way, and then they come back together to form ammonia and water. So that they have that equilibrium sign when they're weak electrolyte. Okay, the non-electrolytes are not going to dissociate. So they may dissolve, but they won't dissociate. So here we have ethanol. Okay, when I put ethanol into water, it dissolves. But you can see there, no ions are produced. Okay, so here's my beaker. And I'm just going to get a bunch of methanol molecules in the water. Okay, so if you think about it, methanol is a covalent compound. So non-electrolytes are covalent compounds because they do not have ions, right? They're formed by sharing electrons. So covalent compounds have non-metals only. Okay, non-metals. They don't have ions. So when we put them into water, they may dissolve, but they will not form ions because they don't have them. So non-electrolytes are covalent compounds. Okay, we're going to use the solubility table now to predict if a compound is soluble or insoluble in water. So you have that solubility table in your handouts under the Chapter 4 module. Make sure to print that out because you're going to be needing it for your recitation worksheet as well as your homework. And that's the table I'm going to provide for you on the test, okay? So if something is soluble, it's going to dissolve in the water. If something is insoluble, then it won't dissolve in water, okay? So let me just give you the definition real quick of solubility. Okay, so solubility is the amount, let me write this down. I'm just gonna write solubility. Okay, here's the definition. Solubility is the amount of a substance. So the amount of a substance that can be dissolved in a given quantity of solvent. The amount of a substance that can be dissolved in a given quantity of solvent. So you can only dissolve so much, right? So if I'm making lemonade with the Country Time lemonade powder, and I really like my lemonade strong, and I dump a bunch of powder into the water, eventually it's going to stop dissolving, right? The solvent can only hold so much solute. So it's the solubility of the water, or it's the solubility, it has to do with how much the quantity that can be dissolved in that amount of solvent. Okay, so here's our solubility table. So you're going to have this on the test. You just need to know how to use it. That's all. Okay, so the first top part here, so we have soluble ionic compounds. There's two parts to this table, and then insoluble ionic compounds, okay? So we're going to cover the top portion first. So these ions that are listed up here are soluble in water. Okay, so if I have, let's say, calcium nitrate. Oops. Okay, calcium nitrate. Okay, because nitrate is in this list, it's going to be soluble. Okay, so that's all I have to do. I look at my compound, I look at what the ions are listed here in this table, and it's in the soluble side, so this whole compound is soluble. Okay, there are no exceptions to nitrate, acetate, chlorate, perchlorate, or up here, sodium, potassium, and ammonium. Okay, there are no exceptions to that. Those are always soluble. But now, let me get rid of this. Come down here, and now we have some exceptions. Okay, so chlorine is soluble, bromine is soluble, and iodine is soluble, except when it's paired with lead 2, silver, or mercury 1. Okay, so if I have, we'll just stick with calcium here, calcium chloride. Okay, I come here, I look, okay, chlorine is soluble, calcium's not an exception, so this is soluble. Put an S, okay? But if I have silver chloride, oh boy. Let's try that again. Silver chloride, okay, that is insoluble. Okay, because silver is paired with chlorine, it makes it insoluble. So this side of the table, right here, are the exceptions. So when you have your ion paired with anything over here, it makes it insoluble. Okay, so here we have fluoride is soluble except when it's with calcium, strontium, barium, and lead 2. So CaF2 is insoluble. But up here we saw, no, let's not use that one. But let's say potassium fluoride, Kf. Now that would be soluble. Okay, so you just have to look at what's in your compound and use the table to figure out if it's soluble or insoluble. Okay, then sulfate ions are soluble. And it has the same exceptions fluoride had, except also barium is in that list. So calcium, mercury 1, strontium, barium, and lead 2 all make it insoluble. Okay, now the second part of the table are insoluble ions. So hydroxide and oxide are insoluble, okay, except when they're paired with sodium, potassium, and barium. So these exceptions over here make them soluble. So it's just the opposite, okay? So these are insoluble unless paired with the exceptions, then they're soluble. Okay, sulfide is insoluble. So here's sulfide, it's insoluble unless it's with sodium, potassium, ammonium, or barium. Okay, and then carbonate and phosphate are insoluble except when they're paired with sodium, potassium, and ammonium. So again, you will have this table. Just make sure you know how to use it. So let's do these right here. So have your solubility table. If you don't have it, pause this and go print it out and then come back. Okay, so the first one is magnesium bromide. So we find bromine on our list. Okay, it's at the top. Bromine is soluble and magnesium is not an exception. So magnesium bromide is soluble. Okay, then lead 2 iodide. So iodine is soluble, right? It's right there with bromine. But lead 2 is the exception. So because it's paired with lead 2, it makes it insoluble. Okay, then ammonium carbonate. So carbonate is at the very bottom of the table. Carbonate is insoluble, but if you look at the exceptions, NH4 ammonium makes it soluble. Okay, and then we have strontium hydroxide. So hydroxide is insoluble, so it's that first one listed for the insoluble ionic compounds. And strontium is not an exception, so this will be insoluble. And then zinc sulfate. So sulfate is the last one in the soluble ionic compounds. Zinc is not an exception, so it's soluble.